All right. Good evening, class. So I'm recording this Wednesday night, the day before the day that we are resuming the college opening. Your class is, of course, on Thursday at 2 o'clock, and so you should be getting this via either my courses or YouTube. So I'll be putting it in both areas so you can see it. And again, well, first off, I want to hope that everybody fared well from the storm. I know probably 99% of you guys were affected by the storm, either some kind of damage. Um, Almost all of you guys, including me. I live in Manatee County. Was affected by power outages, and we see how dependent we are on electricity. So anyway, I wish you well. I hope everything uh, fares out for you in the long run here. But yeah, we need to kind of get rolling again. And um, this message or this video is in lieu of our class, which would have been on Thursday, October 17th. And this will be an asynchronous class for this week, just to document it that it's tied to the effects of Hurricane Milton. All right, so you'll see um, once I share my screen here, you'll see um, the calendar. I'm going to bring up the calendar and a couple other pieces that we might want to review. I may not have been clear in my prior email, but I've modified the calendar slightly on the right here. Should be able to see it. I don't want to split the screen, but we are going to be working on the resistor heating experiment, sometimes called the Joule heating experiment. So experiment 7. And this document is going to be due next week on the 24th. I think I also adjusted another document as well. I think that other document that was going to be due on the 20, the resistor time constant. Some of you guys had some issues with that because of the power. And I modified that to be due on the 24th as well. So that one would have been experiment 6. And so if you had some issues with that, please note that I see only about a third of you guys got that in, because that would have been due on the 10th, and we canceled class that day. And so now here we are on the 17th. So, and also, I think I said this in the email. It's not that I'm trying to brush you off, but it's been really tough. Just like, again, I'm not trying to get any brownie sympathy points, but I'm trying to get everything reorganized here. And unless it's vitally important as it relates to the class and maybe your issues, kind of hold off on the emails, because I just can't get to all the emails. I've been flooded with emails. So anyway, let's get moving here. So there's our new calendar. So you're going to want to look at that, and the document is uploaded. You should be able to see that as well. And let's talk about our experiment. So the experiment is not only called resistor heating, but it's also called Joule heating. I'll make a slight little modification in the title of the Word document so you can see it. You'll see it in all the other documents as well. But basically, in a nutshell, this unit of Joule is named after a guy named James Joule. And if you can look right here, I just kind of pulled up a little picture of what his experiment was. And what his experiment was is fairly, looks fairly simple, but it basically shows that the weight this of mass M is going to produce some energy, and that energy that it uses to move down the cable is also going to be transferred into that paddle that you see right here. It's going to stir the water and in turn create or transfer uh, heat via friction. It's going to heat up the water, and that energy is basically going to be equivalent to the amount of work that is done by this mass to go down this cable. So again, looks very simple, but has had a lot of useful benefits to us in terms of calculating and figuring out how energy is transferred. And so that's what we're going to do today, except we're going to use, we're also still going to use water, but we're going to use a resistor, two resistors here, and we're going to heat up the water via this simulation. So I wanted to show you one more document here. And so this is going to be the document that you guys are going to use to push through this experiment. What's going to be really helpful to you is two things. One, make sure you're using SI units. The units that you see in this simulation on the left are not always SI units. So you should know the various SI units. It's going to be very, very, very important for you to recognize SI units. SI units of temperature are indeed in Celsius. So in the event that you haven't seen that, you understand that that is one unit that you can work with. Sometimes we use degrees Kelvin as well. But for our purposes today, we should be fine with degrees Celsius. All right, and so let's look at this table here. And a couple things that you're going to need to do is you're going to need to make sure that you kind of modify this slightly. So I'm going to probably need you to fill in what these units are. So that omega should be ohms, that S should be seconds. We're going to be measuring unit of energy and or heat. Heat is measured in joules. So you're going to probably want to take that into account. There's a little bit of modification or some character issues here. So that upside down question mark probably should not be there and can be deleted or just crossed out. All right, so looking at the simulator here on the left side, just kind of showing you how this all works. Let's see if I can get this to, all right. So what we have here is, I'm going to try and zoom in the best I can. I'm not sure if this thing will zoom in. Let me pause here for a second. I'm gonna pause and okay, so I wanted to share my screen. I also want to make a correction. I said that degrees Celsius are the SI units for temperature. SI units for temperature are degrees Kelvin. However, the temperature change that you guys are going to calculate, they're equivalent. So you'll see if you look at the scales for degrees Celsius and degrees Kelvin, there's a one-to-one change, if you will, for degrees Celsius and degrees Kelvin. So that temperature change shouldn't matter. So in other words, if you increase your temperature in degrees Celsius from 20 to, let's just say, 50 Celsius, there's a 20 degree Celsius change. And the same thing would occur in Kelvin as well. So you typically don't say degrees Kelvin. So just to be more precise, Kelvin. But that's neither here nor there. So on the right side, what I also was doing is I was looking up. I was making a copy of the simulation. So actually on the left side is the simulation because I wanted to point out a couple things while I move it. So so here's my laser pointer. This is a picture, and so and on the right side is the simulation. So how the simulation works is I'm on the right side here, and I hit the play button right over here, and you'll start to see this start to the temperature begin to increase. All right. And so you're going to do that for the various currents. So you're going to change, actually for the first table, you're going to have the current set at one amp. And that's the default setting right here. And you'll see it in the simulation. I think my screen is just cut off for whatever reason. The other thing that you're going to want to pay attention to is the simulation measures in minutes. So you're going to need to convert that into seconds. Okay. So two things again. SI units for temperature are in Kelvin. The change in temperature is going to be a one-to-one. So the change in degrees Celsius is going to be the same thing as in Kelvin. So you don't really need to worry about that conversion. And then the time piece needs to be modified so it reflects units of seconds. Okay, so our goal is going to be to figure out, you'll see the calculations. I'm not going to go through all of the calculations. You're going to try and figure out how much energy is transferred from that resistor there into the heat, into the water to heat this water up. And now this piece over here, this is another resistor to help us vary and change the resistance of the system. And so let's go back over, see if I can, yeah, so I can take that, turn that off. Let's see if what it's looking like here. For whatever reason on my iPad, I'm not able to show you this piece right here. But anyway, you're going to slide this, you're going to change the resistor, the resistance of this resistor in here. And let's see if I can go into the simulation on my PC. Let's see why. Oh, I guess because the way mine's is set up, the controls are going to be over here on the right side. So let's see if I can refresh that one more time for you. Yeah, my iPad is, oh, there we go. Okay, so one more time, we can change the resistance of the resistor inside the water, which in turn changes the resistance of That outside resistor, we call it a variable resistor, or God, why is it leaving? A rheostat. So this is a rheostat. Just think of the rheostat sort of as um, um, a dimmer switch. So you can use that. And then you can also change the current that is running through that resistor as well. So you'll have to modify each one of those. And then remember, each time it's going to reset, I believe, back to the default setting. So if you hit play and let it run based on what I have it set at, you're going to probably need to change it back to those default settings. And so in this case, the temperature change was 75 degrees Celsius, which is also the same as 75 Kelvin, because remember, it started off at 20 degrees Celsius. Okay, so in order to reset that, you just hit the little curly circle on the top left of your screen. Everything else is going to be pretty much straightforward. So let's see, I just wanted to go back to our picture one more time. In some cases, depending on your PC, on my PC, the controls show up on the right side. On my iPad, it shows up on the bottom. Not a big deal. There's not a whole lot of other, I guess you can change that. I'm noticing there's a little hamburger button right underneath my picture that you guys can't see right now, but it's right in here. And if you change that, it allows you to move where your menu is. So I didn't know that. That was interesting. And so if we go back to the menu, let's see if it works. Oh yeah, you can do it on the iPad. I don't use this a whole lot. So in any case, basically what we're going to be calculating, you're going to figure out the energy that was generated by the resistor in the water, and it's going to be transferred to heat up the water, and you're going to see some similarities, hopefully. I think the key thing for you guys is to make sure you get all your units correct, and I think it's a fairly straightforward experiment. Some of you guys may not be familiar with the units of work or energy. The units of work and energy are measured in joules. When we apply a force to an object, when we move something a certain distance, that is a measurement in joules, also called a Newton meter, but also we can figure out units of energy via a transfer of energy via a joule, and that's figured out by some of the equations you'll see in the document. You'll see an equation that is written using current and resistance and time. So go through that. Go through that document. Make sure you make the slight little modifications before you submit it, and hopefully everything works out fine for you. Again, wish you guys well. I will be online to answer any questions that you have next week. And you guys take care.